So next up in our exploration of physics is the bit that everyone likes. So we're going to start talking about the solar system. So space and stars and all that exciting pretty stuff. So we need to know what's inside the universe. First of all, we just need to make sure we get our terminology right. So the universe is everything. So you can't get any bigger than the universe. It is everything that exists. It is mind-bogglingly huge. Seriously, seriously huge. So, biggest thing ever. You probably can't even imagine how big it is. It's that big. It is approximately 1.3 times 10 to the 26 metres. So that means there are 26 zeros after the 1.3. So there you go. That's it written out. Huge. And because it's that many zeros, if I'm going to talk about it in metres, it means that metres aren't a very useful unit when we're talking about space. They're useful when we're talking about how big a room is, but if we're talking about how big even our solar system is, they're going to get a bit clumsy. So all these zeros, we don't really like them. So what we do is we use a different unit. And the unit we most often use is based on light. So light travels at a constant speed in space. It travels at 3 times 10 to the 8 metres per second. And a light year is a distance, and it's the distance that light travels in 1 year. And that's equal to 9.5 times 10 to the 15 metres. So if you compare that to the size of the universe, it's still not as big as the universe. You still have to do quite a lot of light years to get across the universe. It's approximately 13 billion to get across the universe. But the unit is much, much more useful. So this is why we use light years when we're talking about distance. We can also talk in terms of light seconds and light minutes, so how far light travels in a second, how far light travels in a minute. Those are more useful units for slightly smaller distances. So within the solar system, we might talk in light minutes. If we're talking between galaxies, we're definitely talking light years. So it's just an alternate unit that makes life a bit more easy. So we've got our universe, we've got that it is mind-bogglingly huge. So what's inside the universe? Well, inside the universe there are millions and millions of galaxies. So here's some pictures of some different types of galaxies. They come in all sorts of shapes and sizes and typically look pretty pretty. The galaxy we're in is called the Milky Way, and the galaxy that's nearest to us, we think we're pretty similar to, is called the Andromeda Galaxy. So what's inside galaxies? Well, galaxies are made up of billions of stars. There are also, however, black holes, comets, meteors and planets all inside galaxies. Now, stars are the biggest thing inside galaxies. Black holes tend to be pretty small, although there is the prevailing theory that at the centre of every galaxy there is a supermassive black hole that the galaxy is orbiting, which is quite cool. You don't need to know that for the GCSE, just thought I'd throw that in for you. And then we've got comets, meteors and planets, which are all much, much smaller than stars. So let's start with black holes. The black holes we need to know about are just the remains of very, very large stars. So the biggest stars at the end of their life cycle become black holes. Now they are really, really massive, so they've got lots and lots of mass, but they don't take up much space, so they're very, very small. And it's because they have all that mass concentrated in a small space that they act the way they do. So light can't escape them because their gravity is so strong that everything, including light, gets pulled in. So black holes are actually very small. So stars, I did say stars are large. Just to give you an idea of how large, our star, the sun, is a pretty typical average star. It's not particularly big, it's not particularly small, but it is around 110 times bigger than the planet Earth. So take the planet Earth, 110 of them, and you're about the size of our star. So much, much, much bigger. So around our stars, we've got planets, comets and meteorites, and these will all be orbiting around the stars, so they'll be going around them in circular or elliptical orbits, but we'll talk more about what I mean by that in a second. So for the higher paper, we do just need to know a little bit of terminology about orbits. So we do know planets orbit stars and moons can orbit planets. And the reason things orbit each other is because of the force of gravity. Now, whenever a force makes something go in a circular shape, so if it goes round in a circle, we call that a centripetal force. So in the case of orbits, gravity is the centripetal force. Okay, so our solar system. So we've got our star on the left-hand side, which is huge. This is not to scale, by the way. If you look at the scales on the bottom, it's very logarithmic. So, I mean, here to here is 0.5, and then this is 10. So as you can see, we've clearly not to scale. It's just so you can see them in order. Right, so what is interesting that I want you to see is that we've got sort of groups of planets, sorry. So at the beginning, we've got our 4 planets here at the start, oops daisy. Then we've got the asteroid belt, and then we have another 4 planets afterwards. So that we've got them separated like this is really, really important. So we call them the inner planets and the outer planets, and they're separated by the asteroid belt. Now, you do need to know the order of these. So we go from the Sun out, we get Mercury, Venus, Earth, Mars. Then it's the asteroid belt. Then it's Jupiter, Saturn, Uranus, Neptune. The way I remember the order is my very easy method just speeds up naming. Now, of course, it used to be naming planets, but Pluto is a dwarf planet now, so it's not considered one of the planets. There are only 8 around the Sun. Now, I know people are getting a lot of uproar about this, but Pluto is really just a rock, and there are bigger rocks floating out there than Pluto. It's just, once upon a time, someone made a prediction that there would be 9 planets, so gosh darn it if they didn't find themselves 9 planets. But it's not really, it is literally just a bit hunk of rock. Okay, so need to know the order though. You can come up with any way you want to do it, but if you can remember the first letters, you tend to get the order right. Most people remember that Mars is next to us, so we don't need to worry about the 2 M's, and then we just go through. So my very easy method just speeds up naming. Right, comets. So we need to talk about comets a little bit. Comets are basically balls of ice and dust, and they have what we call elliptical orbits. So this is a picture of an elliptical orbit here. So it kind of looks like a squashed circle, and it's closer at one side than the other. And the Sun is near one edge like that. Now, these can be, don't get trapped into thinking these are 2-dimensional shapes, because it can be at an angle to the orbits of the other planets, and they often are. They have tails when they're near to the Sun, so from the picture you can see when they've got the tail, and the tail always points away from the Sun because it's just the dust and ice that's been melted off at the back and ignited. And they change speed through their orbits. They go really, really fast when they're near the Sun, then they slow down as they get further away, and then as they start to come back closer again, they speed up and then slow down and speed up and slow down. And it's just because the force of gravity is a bit larger on them when they're nearer the Sun, so they travel faster there. But we'll talk about that a little bit more later. Right, meteors. So meteors are basically hunks of dust and rock, really, that comes from space debris, really. So losing the ability to talk. Chunks of rock that are just floating around in space. And the tail is just the dust burning up in our atmosphere. So when meteors come through our atmosphere, the dust trail behind them lights up, just ignites, and we get the pretty trail, and that's what we call shooting stars. Okay, so that's what's in space, but obviously, being the exploring race that we are, human beings have an urge to go out and find out more and explore. But going to space is dangerous, and it's expensive. So it's hard to do, and you've got to make sure that you do it carefully and right. So the choice then becomes, do we send manned missions, so send people up there, or do we send unmanned missions, so send robots to go and collect things for us? So some examples recently of unmanned missions that you may be aware of are Rosetta, which is gone and sat on a comet basically, or dropped something off to sit on a comet. It's trailing a comet that's been going through the solar system. And Curiosity, which is on Mars, and I think it's Discovery, the other one that's on Mars as well. So those are unmanned missions. Manned missions would be things like the Apollo missions, the ISS, so the International Space Station. Those are manned missions. Okay, so manned missions, what do we need to know? Well, if we're sending astronauts anywhere, they need to take food, water and oxygen with them. They need to be living in pressurised environments because we need pressure so we can breathe. If we send them out on EVA, so if we send them outside of our pressurised vehicles, they're going to need really specialised equipment because they need special filters to stop the sun from blinding them because it's unfiltered. I mean, our atmosphere filters out a lot of the dangerous stuff, but if they are just in space, they've got no protection. So they need to have pressurised suits with oxygen supplies. The suits need to be able to cope with temperatures from 120 to minus 160 degrees. Because if you're facing the sun, it's really hot. If you're away from the sun, it is really, really cold. So there are lots of technical difficulties with keeping people safe if we send them into space. There's also that we don't know what happens to people if we leave them in microgravity, so away from the Earth for a long period of time. They are currently about to send up a couple of people to stay on the International Space Station for a year. So normally they stay up for 6 months. These two are going to stay up there for a whole year so that they can study the effects of space on people. And interestingly, one of the people that's gone up is one of a twin, and his twin brother was also an astronaut. He just retired recently, so they're going to use the fact that they're twins to compare these effects. It's going to be a quite interesting scientific study. Right, so that's manned missions. Got off on one there, didn't I? But all interesting stuff you can write about in your exam. Unmanned missions. So think about unmanned missions. We can send them to places we can't send people. So if there is a toxic environment, I can send a probe and no problem. They are, however, very, very expensive. And if I'm sending an unmanned probe, it needs to be robust and reliable. So that means it needs to be able to survive without being maintained or without needing to be repaired. Because obviously there will be no one to do this. And if they get stuck or broken, that's it. They're there, they're gone. Which is a lot of money to leave on the moon. Or on Mars or whatever we're looking at. So these are the considerations we need to talk about. There is no real right answer on this. It's about trying to decide which is the best option for what you want to achieve. And you just need to be able to talk about some of the pros and cons. Okay, so that's it. Wittering done. This was more me telling you lots of exciting stuff, really. So I hope you enjoyed it. And don't panic about the length, because there wasn't that much there, really. Okay, so remember, if you've got any questions, don't hesitate to ask.